Welcome to the first chapter of my series on my personal exploration with squircles. This video is going to be a brief introduction to squircles and base P trigonometry. We're going to start with the equations we can use to describe a unit squircle. I'm considering anything to be a unit squircle if it can be represented by the equation absolute value of x to the p plus absolute value of y to the p equals 1, where p is any positive real number. The language that I use to describe certain squircles is pth degree. For example, a first degree squircle is a rhombus, a second degree squircle is a circle, or a sixth degree squircle is convex. Now, if we convert that to polar coordinates and solve for r, we end up getting this expression, which we will call height base p of theta for hypotenuse. This function is very important. I'd say the most important function in base p trigonometry. Now, taking this polar representation of a squircle, we can parameterize a squircle by multiplying height base p of t by cosine t and sine t. These parameterizations will be called cos base p and sine base p respectively. These functions are also important. You can visualize cos and sine base p as the lengths and heights of triangles inscribed between that pth degree unit squircle, the x-axis, and the y-axis, similar to the geometric visualization of base 2 trig in a unit circle. Here you can also see why I named it the hypotenuse function, since height base p of t is the length of the hypotenuse of this triangle, an identity easily derived from the Pythagorean theorem. We'll define the other 4 trig functions algebraically as analogs to base 2 trig. We'll notice with tangent base p, though, that the height base p's in their definition cancel out, meaning tangent base p equals tangent for all values of p. Using the same logic, we can show that cotangent base p equals cotangent for all values of p as well. For us, that means tangent and cotangent base p will largely be ignored in the future as they're equivalent to their circular counterparts. Speaking of circular counterparts, I've been saying base 2 a lot when referring to our usual trigonometry. That's because when p equals 2, squircular trigonometry becomes circular. If we remember that r equals height base p of theta, we can see that height base 2 of theta equals 1, and r equals 1 is the polar equation for a circle. Next, we have what I call the Pythagorean identities, which can be derived from the definition of hype. Then, dividing the first identity by the absolute value of cosine base p to the p, you get the second one. The third one using sine base p instead. The fourth Pythagorean identity can be derived by adding the second and third identity. Feel free to pause in order to see the whole derivation. And voila! You can see how these identities are analogous to the circular Pythagorean identities using absolute values to the p's instead of squares. So to recap, in this chapter we defined the hypotenuse function along with the other 6 basic base p trig functions. We learned that tan and cot base p are just the same as tan and cot, and we derived 4 Pythagorean identities. See you in the next one!